Hey, it's Dr. J. Today we continue our discussion of indefinite integrals. So this collection of symbols is called the indefinite integral of the function f of x with respect to x. So let's write that down. The indefinite integral of a function f of x with respect to x. And the result of this calculation is another function called capital F of x plus any constant. And so we read the equal sign as the word is. The antiderivative capital F of x plus any constant. C. All right. And again, in my first part of the video, I gave the definition of what it means to be an antiderivative. And I will say, because if you took the derivative of capital F, you would get lowercase f. Or you can write it with this notation, which I kind of like this notation because it matches the dx here. If you took the derivative with respect to x of capital F, you would get lowercase f. And then the plus the constant is because the derivative of a constant is always 0. So when you take the derivative of the right-hand side, you can essentially ignore the plus c part because that will always give you a derivative of 0. So the only actual derivative that you're computing using the techniques of differentiation is the capital F. Right? Although I guess you could say this is also a technique of differentiation, but it's what we call trivial. Its derivative is 0, so there's really not much to it. Okay, well, in the first part, I defined the antiderivative, and I gave some introductory rules of indefinite integrals. So in this part, we'll get right into it with some examples. Of evaluating indefinite integrals. So, evaluate, sometimes I will say find, or sometimes I will say determine, sometimes I'll say calculate. These are all synonyms for do the math, right? Determine the result. All right, so the very last rule, I think I called it rule number 8, was that if you had a constant times a function, you can bring the constant out to the front. Remove the constant. And ignore it, but don't forget it. And then now we'll take the antiderivative we'll determine the antiderivative of x to the third. So that's the power rule. So that'll be x to the 3 plus 1 over 3 plus 1, and then plus any constant. And you don't really need the parentheses. You can use a dot. Or you can just write it like this, 5/4 x to the 4th plus c. So the indefinite integral of 5x to the third power with respect to x is 5/4 x to the 4th plus c. And you could do a mental check. If you took the derivative of 5/4 x to the 4th plus c, you would get 5x to the third. I'm not going to do the math. It's a mental check here. I'll just do the little mind bubble here. Right. You see, 4 times 5 is 20. 20 divided by 4 goes back to being 5. Yeah. Or you can just say the 4's cancel. Then you subtract 1 from the power and you get 3. And then, as I mentioned earlier, the derivative of the constant is always 0. So it goes right back to being little f, lowercase f. There's your lowercase f inside there. I won't do this on every problem, but I recommend you do it on every problem, especially if it was a test or something. All right. So really today's just show day. Show and tell, I guess. Mathematical show and tell. So find the antiderivative, or find the indefinite integral, or find the answer. That's what a lot of folks will call it. What's the answer? Hopefully the correct answer. So this is the indefinite integral of 12x to the negative 5, because the power is in the denominator. X to the 5th power is in the denominator. Again, we remove the 12. I call this rule the bread and butter rule. Yeah, the power rule, your daily bread. You're going to be doing this all the time. I use parentheses just for safekeeping. I usually end up removing them. You add 1 to negative 5. Be careful. When you add 1, negative 5 then becomes negative 4. So now we have negative 12/4 x to the negative 4 plus c, or negative 3 x to the negative 4 plus c. You could also write it this way, negative 3 over x to the 4th plus c. These are equivalent. I'll accept either one of these. Now, if you rewrite it and you rewrite it incorrectly, then you'll wish you probably would have just left it alone. Notice the negative 3 remains in the numerator. I guess you could do this. You could put the negative out in front. That would also be correct. And there you go. Let's keep moving. Yeah. Sometimes we just say the integral. Another way to say this as sort of an action verb is to say integrate, or perform the integration. All right, now we're getting multiple terms. So we have the integral of a sum. Well, that's another one of those introductory rules. That is the sum of the integrals. The constant comes out in front. Interesting. I only pull the constant out to the front if there is another function that it's being multiplied by. Since this constant is all by itself, I usually don't bother pulling it out. If you did remove this constant, it wouldn't be incorrect, but then you'd have to put a 1 right here. It means the same thing. All right. Now remember, this is one of those special cases. The derivative of e to the x is e to the x. So therefore the antiderivative is also e to the x. And then the antiderivative of 1 is just x. Normally I skip this step and I just jump right to here. So I say the integral of 9 with respect to x is 9x. All right. And then don't forget your plus c. So your final answer is 7 e to the x plus 9x plus c. All right. We're going to make a lot more progress today because we've seen all the inner workings of how this works. So now it's just practicing or exercising the principles that I've demonstrated. Okay, so determine the integral. Integrate. So the integral of 9x to the 5th, well, that'll be 9 times the integral of x to the 5th minus 6 times the integral of x dx. These all have dx's, plus the integral of 10. I'm going to work backwards. The integral of 10 is 10x. The integral of x is 1/2 x squared. Yeah. Or you could say x squared over 2. Same thing. The integral of x to the 5th is x to the 6th over 6. And then bring down the constants. 9, -6. This one, the 10 comes down with the x. And then don't forget your plus c. You could actually wait on the plus c till the very end, but if you wait too long, you might forget. So let's put it there now. All right, now simplify these if possible. So 9/6, that'll be 3/2. Yeah, 9 divided by 3 is 3, and 6 divided by 3 is 2. It's as good as it gets. -6 divided by 2 is 3. 3x squared plus 10x plus c. And that's it. When I first learned this technique, you know, I had done math for a very long time, worked my way up to calculus. Many years ago in the late 1980s and the early 1990s, this actually wasn't taught until the second semester of calculus, believe it or not. So we've come a long way now for those of you that are taking this as your very first calculus class. This is done very early in the first semester of calculus. So, you know, by the end of the first couple of weeks, you're doing this. But I still remember to this day looking up at the board, you know, and watching my instructor teach this and go, wow, you know, this is calculus? Like, I was just so amazed because it doesn't really seem that hard, right? It's just, you have to pay attention to the details. You probably could, you know, if you're watching this video now, hopefully you are watching this video, you wouldn't be hearing me. You could probably read the question on the screen and just simply type this in as the answer, right? So even though I notate every step and I'm a real stickler, advocate of principles and procedures, I still, you know, rely a lot on mental math. Especially when it comes to checking answers and things like that. Okay. So yeah, this is calculus. This is integral calculus. Back in the day, we used to separate them out, differential calculus and integral calculus. We still do some separation in some of the other levels, but for Math 9, those of you that are in my business calculus class, this is a one and done calculus class. There is no part 2 to this course. And so we're taking you all the way to the end of the road here. Okay, so evaluate the integral. You might wonder why we call it indefinite. Well, if we call something indefinite, you can guarantee that in a couple days we're going to learn what definite is or definitive, right? This is indefinite, and what makes it indefinite is that we don't have boundaries, right? We don't have defined boundaries, so it's indefinite. You could just simply at this point, since it's the only integral you know, you could just call it the integral. It's a very common symbol. You see it anytime you watch a movie where they do math or science or even a television show, you can pretty much guarantee that symbol will show up somewhere. Sometimes they try to make it look really fancy and scary or something like that. I feel like the more I draw it, the worse it gets. So I just do a stretched out S. And I will explain later in the chapter why we use the symbol that looks like an S. All right, again, now try mental math. See if you can just guess the answer right now. If you do, write it down, sort of. I'll leave that to you if you want to guess. Guess now. We'll see if you're right. So I'm going to follow all the steps. So we're going to do the integral of 7 over x. I can remove the parentheses now. And the integral of 5x. So that'll be 7 times the integral of 1 over x plus 5 times the integral of x. This was a special recipe that you just have to memorize. Right, so there's really no steps to calculating that. You just have to memorize 1 over x is the same as x to the negative 1. And so you just memorize that. And then 5 times the integral of x. We just did that. It's x squared over 2. You can use a dot or parentheses or whatever. And then don't forget your plus c. So now check your guess. See if what you thought it was is exactly what I got here. And the goal is that you can read the question and write the answer, at least for the introductory section of this chapter. They will get more complicated, which is one of the reasons why I demonstrate proper step-by-step procedures, because if you only guess, and that's the only way you know, then adapting a step-by-step procedure becomes very difficult later in the course. So practice the principles now, and your life will be a lot easier later. Okay, so moving right along. 2x to the third minus 4 over x plus 2 over x squared plus 6 square root of x dx. Oh, that's a monster. Well, how do you defeat a monster? One step at a time. Yeah. Or there's an old proverb, how does one eat an elephant? The answer is one piece at a time. As soon as I heard that proverb, first of all, it didn't really make sense, to a young person that's never seen an elephant other than a zoo. But the secondary thing, even if you have seen an elephant in the wild, why would you want to eat one? It just seems like a weird thing to do. So let's go ahead and break it down. So we're going to pull out the negative 2 and integrate x cubed. As I'm writing this, you could probably continue what the next step would be. Negative 4 comes out, and then we'll integrate 1 over x. And again, you could jump to the next step. The 2 will come out, and we'll integrate 1 over x squared. And the main reason for pulling out the constants is so that they don't interfere with the calculation. So you don't use them to determine what the antiderivative is. Those constants just wait until you've performed the integral, and then once you've done that, you multiply the two together. Okay, oh, you can rewrite this one as x to the negative 2, and then you can rewrite this one as x to the negative 1. Or you can leave them as fractions. It's really up to you. It won't change the answer. The same answer either way. All right, so now we do the integration, term by term by term. Each one has its own integrand. So x to the third, that'll be x to the fourth over 4. And I'm just going to use a dot for multiplication. X to the negative 1, that's a special case. That's ln. That's the special one. All right, x to the negative 2. Now they got to be careful with this. You're adding 1. So that's going to be negative 1 and then divide by negative 1. These two are very easy to get mixed up. All right. So let's just focus on them for a second. This one starts off, we call this the integrand. The integrand is x to the negative 1, right? Then the result, or the integral, also known as the antiderivative, is ln. Ln absolute value x. However, this one, the integrand, is x to the negative 2, which becomes x to the negative 1. Right? It does not become an ln. It stops right at x to the negative 1. And then don't forget you're dividing by whatever the new power is. And I'm going to use a dot for multiplication. Okay, here the integrand is x to the 1/2. So the integral is 3/2 and then divided by 3/2. And then plus c. So this one, if you can read and guess the answer or mentally calculate it, I guess I probably shouldn't call it guessing because you're doing a little bit more than that, that you have a very good sense of mental calculation. So that's good. I encourage you to do that as much as you can. All right, there's an equal sign right above my head. So negative 2 and 4 would be negative 1/2 x to the 4th. Be careful. I have seen people go negative 2 and 4. They'll divide them and they'll accidentally put negative 2 here. It's negative 1/2. Or you can write it this way, negative 1 and then over 2. That's the same thing. This one, you just 4 ln absolute. I'm just removing the dot. Here, we've got a positive 2 and a negative 1. So it's going to be a negative 2. And then I'm going to send this down to the bottom over x. Here, I'm going to flip and multiply. So it's going to be 2/3 times 6. That's 4. Right? 2/3 times 6 over 1. That's your brain on arithmetic here. So you're going to flip 3/2, it becomes 2/3, and then the 6 is 6 over 1. So 2 times 6, I shouldn't have to tell you this. It's 12 divided by 3, which is 4. Now you can either leave it as 3/2 or you can write it as the square root of x cubed. I'm going to go ahead and just put my final answer here. 1/2 x to the 4th minus ln absolute x minus 2 over x plus 4 square root of x cubed plus c. There's your final answer. So notice progressively getting deeper and deeper into the material. And we progress. So we've started with single term integrals. Then we have multiple term integrals where we just take them term by term. But you might notice that there are two rules missing. There's no product rule for integrals. And, I wish I could tell you there is a product rule. We just haven't learned it yet. That's a classic math teacher trick, right? I make you do it the hard way, and then after like 2 weeks of that, and you've seen me do this in the past, right? You've been with me for a couple months now. I make you work really hard at something, and then I say, there's an easier, softer way, right? There's another way. Unfortunately, this is one of those things that I'm not hiding anything from you. There just is no product rule for integrals. There are techniques that we will develop to address this problem. So I don't want you to misunderstand and think, there's just no way to do this problem. It's just there is no quick rule like there was for derivatives, right? So that's a bummer. And so in my next example, am I up to 7? I guess so. Yeah, flying through. If I have the integral of 7x to the third times 6x squared minus 4. So this is your f of x, and this is your g of x. There is no easy rule. All right. It doesn't mean that it's impossible. It just means that you can't do some integral of this times the integral of that. It's just simply not that easy, right? So you must rewrite it first. And I will put the terms rewrite in different, in quotes. I don't mean always rewriting it the same way. In this particular example, I just mean distribute. That's what I mean by rewrite. There are lots of different ways of rewriting. So first we're going to distribute this. In other words, rewriting it without the product. And then applying the rules that we've learned in the previous section. And I've been demonstrating in this section. So that'll be 42 integral of x to the 5th minus 28 integral of x to the 3rd. And just do them one at a time. So 42 x to the 5th will be x to the 6th over 6. I'm putting a dot for times. X to the 3rd, that'll be x to the 4th over 4, and then plus c. So the final answer will be 7x to the 6th minus 7x to the 4th. Oh, that's a coincidence. Plus c. They both came out 7s. 42 divided by 6 and 28 divided by 4. I didn't even plan that. Lucky 7s. Okay, so we're going to have to deal with these on a case-by-case basis. This is certainly the easiest case. This is, we call the mono times a poly or a binomial. A binomial is the smallest type of polynomial. I guess you can consider a monomial, sometimes we call it a degenerate polynomial, but whatever. It's one term times 2 terms. That's what I mean. That's definitely the easiest case. They do get more complicated. So let's do another example. Well, I might need the whole board for this example. So example 8. At this point, I'm not even writing directions down because all of these are the same directions. Until we get one that has different directions, there's no need to do that. All right, so this would be binomial times binomial. Let's go ahead and do it, right? Before you can integrate, you must first rewrite it. So we'll go 9 times 5, x times x to the 4th. That'll be x to the 5th. And I'll do negative 10 times 5, so that'll be negative 50 x to the 4th. Then I'll do 9 times 2, so that'll be 18x. And then I'll do negative 10 times 2, which will be negative 20. And I really don't need the parentheses anymore. I've dispensed of them. And now we can march down the line term by term. Let's double check all our signs. 9 times 5 is 45. Check. Good. If you make a mistake, it's usually a sign error. Negative times a positive, negative 50. Good. I'm just double checking my signs. Positive times positive is positive 18. And negative times positive, that's the one I was really double checking, is that one's negative 20. Good. All right, I'm ready. You want to check early and often. If you wait till the very end to check, you could end up doing the whole problem over again. Okay. Term by term. Piece by piece. Integral of x to the 5th, x to the 6th over 6. Integral of x to the 4th, x to the 5th over 5. Integral of x, x squared over 2. Integral of 20, 20x, and then plus the constant. Call that the constant of integration. 45 divided by 6, that'll be 15 halves. Right? 3 goes into 45 15 times. 3 goes into 6 2 times. You could also write 7.5. It would mean the same thing. 50 divided by 5 is 10. 18 divided by 2 is 9. And we are done. I say this a lot. I don't know if I've said it a lot in this course, but I have said it a lot in my career. Not every problem is a problem. Yeah. Some problems are just opportunities, a chance to show off a little bit. So there you go. And this is a classic example, to impress your friends and family. If somebody didn't know calculus, never watched one of my lectures, never watched any lecture, never read a calculus book, never been to college for that matter, this would look pretty impressive, right? But for those of us that know, for those of you that know, welcome. I'll teach you the secret handshake after you pass the class. All right, you're in the club now. I'm not going to go much further than that in this lecture, but you can imagine these could get more complicated. We could have trinomials, right? Trinomials have 3 terms. Anything bigger than 3 terms, we just call it polynomial generally. You could have larger exponents. You could even have exponents outside of the parentheses. But that's a bridge we will cross at a later date. Since there's no product rule, there's also no quotient rule for integrals either. So if I give you a function divided by a function, there is no easy rule for performing the quotient. So suppose the numerator function is 7x plus 9, That's your f. And the denominator function is x squared. You must rewrite it first. So there's no nice, easy way to say it. I mean, I wish there was. We could say, oh, just take the integral of the top, take the integral of the bottom, and divide them or something. Or maybe even a more complicated rule like what we had with derivatives, right? Remember the one with derivatives was like the top and then the bottom and then minus the bottom and then the top and then all over the bottom squared, right? I mean, you could have some fancy recipe like that. There's no nice recipe. There's not even a not nice recipe. So again, I'll put the words rewrite in quotes. We don't always rewrite them in the same fashion. It depends on the type of problem. This is again binomial on top and monomial on the bottom. So one term on the bottom, two terms on the top. So the way we're going to do it is by separation. Like that. In other words, if the denominator only has one term, then you can separate into two individual terms. Each one of them has the same denominator, x squared, and handle them separately. So 7x over x squared just becomes 7 over x. Right, here, I'll show the math. I know you don't need to see it, but maybe you like it for your notes. You cross off the x on the top and then cross off the squared on the bottom and you get 7 over x. And then now handle them separately. We've done a lot of these today, so I'm just going to jump right to the answer. This will be 7 ln of x. And this will be 9x to the negative 1 over negative 1 plus c. So the final answer is 7 ln absolute x minus 9 over x plus c. Notice the dividing positive and a negative changes this sign to a negative. And then the negative 1 power, I just send it down to the bottom and make it a fraction again. I can't get the whole thing in my screen, so I better just stop there. Huh. My numbering is off. It's all right, whatever. I don't know. I either skipped a previous number or I did 10 twice, but either way, I want to get back on track. So I think I skipped a number. Does it really matter? I don't know. I always like to tell stories about when I was in college. Now, I mean, not every professor in college is the same, but it was very common, 30 years ago for professors not to number anything, right? So it was just example, 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 and nothing was numbered, and it'd be left up to the student if they wanted to number things. Some professors numbered. Some professors had really complicated numbering systems. Now I'm doing Dr. Jordan's story time, Back when I was a kid, back when I was your age, it was an uphill walk to school both directions. And when you got to class, the professor did not number the problems. Or if they did number the problems, they do like this: 2.1.1.5, 2.1.1.6, 2.1.1.7. They'd use these ridiculous numbering systems that almost like the Dewey Decimal System. And if you kids don't know what the Dewey Decimal System is in the age of the internet, Google that and you'll know exactly what I'm talking about. So I digress. I'm calling this example 10 again. Example 10 again. It's very similar to the last example 10, so I will spare you the long discussion, and I will just show you that so far the only type of quotient that we are prepared to do today is the type that have one term in the denominator. And we need more techniques to get any deeper than that. I also want to show you that I'm going to save a line of my paper and write all the square roots as half powers to the 1/2 power. So I'm kind of doing two steps at once there because I'm looking at my board here and realizing I'm running out of room. Okay. All right, so now we got the integral of 4x to the 3/2, the integral of 6x to the 1/2. Remember, there's an invisible 1 here, so you're going to subtract those. And then 8x to the -1/2. All right. And I could write 3 separate integral symbols, or I could just write it once and then do it 3 times. It's the same thing. Okay, I'm just saving space. If I really wanted to be proper, I would go like this. Maybe I will, just for your notes. Yeah. So breaking it up into 3 individual problems. The problem with the problem is that you have to write the dx 3 times when you do it this way. Each integral symbol requires its own dx symbol. They go together. Right, they're a pair. All right, now let's do it. So it's going to be 4 times, remember we're adding to this, so that'll be 5/2 and then divided by 5/2. We're adding to this, so that'll be 3/2 and then divided by 3/2. And then we're adding, so that'll be x to the 1/2 divided by 1/2, and then don't forget your plus c. And then remember, when you divide by a fraction, you're going to flip and multiply. Flip and multiply. All right, all 3 of these. So flip that over. It's going to be 2/5 times 4. That'll be 8/5. All right, flip this one. It'll be 2/3 times 6. Hey, we've done that one before. 2/3 times 6 is 4. Coincidence. I didn't plan it that way. 1/2, we flip it, it becomes 2. Or 2/1, so that'll be 16. And that is your final answer. Or, if you want to be a real show-off, you want to make it look real fancy, you write it like this. 8 times the square root of x to the 5th over 5 plus 4 times the square root of x to the 3rd over 1. You don't have to put over 1. Plus 16 times the square root of x plus c. There you go. Personally, I would probably just leave it like that. Every once in a while, just to demonstrate that you know it, or that maybe it's got a pop-up menu where you could do the square root symbol. Sometimes that's quicker than trying to type these fraction powers. You're going to be doing all this with your keyboard, so do whatever is efficient for you in the time that you have. Speaking of time, we have enough time to do some applications of this, or we're going to do one application, and then I want to show you how to find C. Right. So before I do any more examples, let me just talk about what is the meaning of C. I think you already know that. It means constant, right? We use C for constant. We also use K for constant. C and K are some of the more common variables or letters that we use for constants. A little fun fact, the word constant in German starts with the letter K. So constant with a K. So what is the meaning of C? Well, let's go back to the first part of this lecture where I was talking about antiderivatives. Yeah. There are many possible antiderivatives, right? So let's just, and I'm not going to number this one. So this is, again, old school. So e.g., for example, I'm not going to give it a number. If I said, the antiderivative of x squared. Again, that's always my go-to when I want a real easy example. Right? You can do the same thing, right? You want to explain to your relatives or friends, that, oh, I'm taking calculus. And maybe they care. I don't know. Every once in a while, you'll find one person out there that actually cares. How could you explain something complicated, very easily? Well, this is the go-to. Yeah. Give them a parabola, because it's a very easy shape to understand. And you can explain things. So what is the antiderivative of a parabola? Well, it's a cubic, right? It's not just any cubic, it's 1/3 x cubed, plus c. So what this means is that every function f of x equals 1/3 x cubed plus 1, or f of x equals 1/3 x cubed plus 2, or, and I'm using subscripts here, this is what we call a family. Don't they look like a family? They're all related, right? And how are they all related? If you took the derivative of any of these, you would always get x squared. Oh, we'll call this C. So no matter what the plus C is, for every possible value of C, every single one of these, they all belong to the same family of antiderivatives because they all have something in common, and that's that they all have their derivative equaling this function, x squared, which we call the integrand, right? So the antiderivatives all have that in common, all right? So what does that look like on a graph? Right. Well, I'm not going to draw it very nicely. I'm just going to sort of squiggle them, right? They look like this. This would be 1/3 x cubed plus 0. By the way, that's also in the family, because the constant could be 0. And then there's another one right here. 1/3 x cubed plus 1. Right? It would pass through this point here. 0, 1. This one would pass through 0, 0. Etc., etc., etc. If I had a big enough piece of graph paper, I could show a lot of them. The next one. 0, 2, 1/3 x cubed plus 1. Oh, plus 2, sorry. Right? So on and so forth, right? The next one will be up here. 0, 3. Right? I'm running out of room. You could even have negatives. Yeah, that would be okay too. That would be 1/3 x cubed minus 1. So even though we say plus c, c could be a minus, right? Now, you could, raise your hand if this were a live class and say, Dr. Jordan, would it be okay for me to say plus or minus c? And I'd have to say yes, it would be. But it wouldn't be necessary. But it wouldn't be wrong. It would just be unnecessary. When you say plus c, it is implied that the c could be either positive or negative. So, for example, if the c was negative, I would say plus -1. So that would be the proper way to write it if you really wanted to, clarify that it's plus a negative, right? But it's just not necessary, but it's still true. All right, I think I've talked enough, all right? This is what the family looks like, right? So, therefore, if we are given 1 point, that's all we need, 1 point on the graph, then we can determine the value of c. Right? So if I gave you this point, 0, 1, then I would erase all of these. And I would say that is the particular member of the family that I'm looking for. Right? But we have to be given 1 point on the graph, and then we can hone in on exactly which member of the family we're looking for. So this is a specific antiderivative. Finding the specific antiderivative. So I give you the derivative, and I tell you 1 point on the graph. Oh, sorry, I wrote down the wrong one. Starting with a much easier one. All right. So the antiderivative, I'm now using lowercase f instead of capital F. That drives me crazy, but it just means that my integrand is f prime. Right. I will mention this means the same thing as lowercase f and then using a capital F. And I admit, even as 30 years of doing this, more than 30 years, it still kind of drives me crazy when there's these different versions of F. But you get used to it. So here's the thing to look for. If the problem gives you f prime, then that is your integrand. And then lowercase f becomes your antiderivative. All right. If you're given a lowercase f without a prime, then that would be your integrand. And then the antiderivative we would use capital F. And I think in part 1, I used both notations. So in this example, I'm using this notation, which I prefer this one because you don't have to worry about the 2 different types of Fs. Okay. It really doesn't matter because you're going to replace your f prime with this anyway. So that's going to go away very quickly. All right. And then this is going to be the result of what you get after you've integrated. Now, we just did a ton of these, so let's do it very efficiently. It's going to be -8 and then x cubed over 3 plus 6x. Yeah, that's it, 6x, integral of 6, and then plus c. Okay, and then now plug in x equals 0. And set it equal to -6. All right. Now you can put the -6 here, or you can put it over here. It really doesn't matter. All right. Don't do both, though. So just do one of them. So I'm going to go -8 times 0 cubed over 3 plus 6 times 0 plus c equals -6. 0 plus 0 plus c equals -6. So c is just -6. By the way, if the input number is 0, it's very common that the c is just this number. It's not always 100% though. It's very common though, so like more than 90% of the time. Although I shouldn't really put a percentage on it because I don't know how many problems you'll do, but if I gave you 10, this would happen 9 of the 10 times. I don't think I would give you 10 of these, but anyway. All right, and so what's the final answer now? The final answer is putting this all together by finding the specific antiderivative. So the answer is this, f of x, -8x cubed over 3 plus 6x minus 6. And that is your specific antiderivative. Okay. Let's do another one. Let's do one where the c is not so easy, right? A little bit harder. Now, the c is never going to be like, impossible to solve. I wouldn't give you that type of problem, but sometimes it's a little bit trickier. So find f of x given f prime of x is, let's do another parabola. This is like the go-to. And f of 3 is 5. Okay. So we integrate f prime. So that'll be the integral of x squared minus 2x plus 4, which will be 1/3 x cubed minus 2x squared over 2. Those 2's are going to cancel. Plus 4x plus c. Or you could write it this way, x cubed over 3 minus x squared plus 4x plus c. Now you plug in x equals 3, and you get out 5. Right, it's technically a y. Right, your outputs are always y's. I don't usually write the letter y here. But when I was drawing the graph a minute ago, this represents the y value. So let's plug in 3. I should probably use parentheses to be good-mannered in my mathematics. So 3 cubed is 27. 27 divided by 3 is 9. 3 squared is 9. 4 times 3 is 12. The 9s will cancel. I'm run out of room here, but I have 12 plus c equals 5. So c will be -7. Just jumping over here to show you that. All right, and then so my answer then is finding f. So f, then go back to here. This is your f. F is the result of the integration, also known as the antiderivative, and then replace c with -7. So x cubed over 3 minus x squared plus 4 minus 7. Yeah. Or you could say plus -7 at the end. Nobody ever does. I don't. But it's technically plus c. And that's what the c came out to be. All right. Not too shabby, huh? Let me do a couple exceptional examples. Things that don't quite fall into the pattern of everybody else. Something that's not just a square, parabola, or a cubic. Let's do an exponential. So find f of x such that f prime of x is 6e to the x minus 7x, and f of 0 is 1. All right, so this is very similar to example 11, I guess, is what I was up to, or 12, depending on who's counting. But it's an exponential function, natural base e, and so we got to be very careful when we're plugging in 0. So let's go ahead and do the problem, or do the integral first. So we got the integral of -6 e to the x minus 7x. I don't really need the parentheses, but they don't hurt. All right, so the integral of -6 e to the x is just -6 e to the x, right? Remember, the -6 would pull out in front, and then the e would just stay e. Now, that's not true for 7x. 7x becomes 7x squared over 2, right? And then plus c. And then now I'm going to plug in 0 for my input. And I'm going to put 1 as my output. And c is what I'm looking for. Now we need to be careful, because when you plug 0 in, the middle term turns to 0, but this e turns into 1. E to the 0 turns into 1. And I can't tell you how many times I've seen students go like this and just cross them out, right? Well, you can do that as long as you know that this canceling becomes 1 and this canceling becomes 0. There are different types of cancellations. Right? So this just becomes -6 plus c equals 1. The 0 doesn't matter, obviously. And then you're going to add 6 to both sides. So your c is 7. Put it up here where everybody can see it. All right. And then remember, once you found your c, you got to go back to the part where you took the derivative, the antiderivative, right? By the way, you could check your final answer. I haven't done that in a long time, but maybe now would be a good time to check and give your final answer as a function. So your final answer is -6 e to the x minus 7x squared over 2 plus 7. So for a mental check, you want to make sure that the derivative of the antiderivative matches. So the derivative of -6 e to the x, that's -6 e to the x. The derivative of -7 over 2x squared, you would multiply by 2. The 2's would cancel. You get -7x. That's good. And then the derivative of 7 is 0. You could also check that if you plugged in 0, you would get 1. Right? That's this input-output relationship, which I'm not going to ask you to graph these. I mean, I would if we had, an in-class graphing session. I'd pass out a sheet of graph paper, or maybe ask you to bring your own. But I'll just say do it yourself. Take out a sheet of graph paper and draw a curve. Or you could type it into a online graphing calculator and get an idea of what this looks like. You will see that it does, in fact, I'm not lying, it does, in fact, pass through the point 0, 1, or right on the y-axis there. All right, well, the only thing left in this video is a second derivative, which we haven't done in quite a while. Since we learned about the antiderivative, how does a second derivative play into this? And the answer is you would need 2 points. So find the function g, just for variety. It's no different than an f. Given that the second derivative is a constant, and 2 points on the graph. G of -1 is 1/2, or 0.5, and I need a second point. G of 1 is 8.5. So if you have a second derivative that's given, you need 2 points on the graph to find the function. You'll also need to do the antiderivative twice. So we start off by doing, so let's just write our plan first. We'll do the antiderivative of the second derivative, and that will give us the first derivative plus the first constant. Then we do the antiderivative of the first derivative, and that will give us the function plus the first constant times x plus a second constant. Then we will use 2 points to solve for C1 and C2. So that is our plan of attack. Take the integral to find the first antiderivative, then take another integral to find the second one, and that gives you 2 constants. We'll call them C1 and C2, or you can call them C and D. That's another way to do it. If you don't like subscripts, you can call this one C and then call the other one D. Same thing. In fact, I think I'm just going to do C and D. Why not? It's the same thing as 2 different C's. Just the other one's called D. That's all. All right, that's our plan. Okay, now, fortunately, we have a very easy second derivative. Right? So this is kind of like a differential equation in a sense, right? It's an equation involving first and second derivatives. It doesn't quite get that official title, but it's leaning in that direction, right? It is leaning in that direction. This concept may come back if you stick around and take more math after this semester. I don't know. I don't know what you're going to do. I'm going to need this space, so why don't I just write over here all my givens. You've seen me erase these before and then panic when I'm looking around in my notes and my board for the stuff that I'm trying to save. All right, everybody understand the plan? Speak now or comment if you don't, I guess. I do read the comments. All right, if you're watching this in real time, I could probably change screens. I'm not going to, so I will check after I'm done with this lecture. So what is the integral of 3? That is 3x plus c, right? That was pretty easy. Yeah. So that is our first derivative. Now we're going to take the integral of 3x plus c, which will be 3x squared over 2 plus cx plus d. And we will plug in both of these points one at a time. All right, so the first one, 3 times negative 1 squared over 2 plus c times negative 1 plus d equals 1/2. That's our first equation. Sorry that I'm cutting off the board here. Second equation. I'm using this point. So I've got 3 times 1 squared over 2 plus c times 1 plus d equals 8.5. All right. Now I need to solve these. Needs a little cleanup. Let's do some cleanup. So 3 times negative 1 squared divided by 2. Remember, you do the exponent, then the multiplying, and then the dividing. So that's going just to be 3/2, which I think I'll just write as a decimal, 1.5. All right, the negative squared will go away. And then minus c, negative and a positive, plus d equals 0.5. And then this one's also 1.5 plus c plus d equals 8.5. All right. Let's add these together like this, and you're going to get 3.0 plus 0, the c's will cancel, plus 2d equals 9.0. Or if you like, 3 plus 2d equals 9. You can take two equations with two variables, stack them on top of each other, make sure you line up the appropriate columns with the appropriate variable, add them together. As long as one of them is negative and the other one is positive, which is by design, that will happen, you get a 0, and that eliminates one of those variables. If you took a high school algebra or a college algebra course, we call that an elimination method. So now just solve this, minus 3 from both sides You get 2d equals 6. Divide by 2, you get d equals 3. All right. Go back to one of these equations. Just pick one. I'm picking 1.5 plus c plus d equals 8.5. Bring it down here. It doesn't matter which one you pick, right? So make sure you save these after you've canceled them out. Don't erase them. And then just pick whichever one looks nice to you. And then put the d in. We know that d is 3. And then solve this. So we got 1.5 plus c plus 3 equals 8.5. So 4.5 plus c equals 8.5. So it looks like c is 4. So remember, our answer was g of x equals 3x squared over 2 plus cx plus d. So c is 4 and d is 3. And that is your final answer. That was kind of new. I mean, that was like old school algebra mixed with differential calculus, first and second derivatives, also mixed with the new integration methods that we've learned. And I don't think I'm going to have enough time to do the business math problem. So check back soon for a one problem video. It's kind of a doozy, so I'll save a spot for that because I got to put the business back in business calculus. All of these techniques we're learning have a goal in mind, or several goals in mind. One in particular is, we talked about it last time, profit, revenue, cost. Those are the three functions that we've talked quite a bit about. So until next time, I'm Dr. Jordan, and I'll see you on the internet.